It's time now to look at finding the volume of a function of a solid given the use of what we call cylindrical shells. Now imagine, the best way to describe it, and we talked about the idea of an onion in class. The idea is like you have an onion that you peel back the layers of. That's what a cylindrical shell's like. The other one that comes into mind is the idea of stacker cups. If you know those stacker cups, like you can stack smaller ones inside the larger ones, and together they make a whole volume of something. But it's really just, if you take them out, they're like those cylindrical. They're a cylindrical shell that stack inside each other. So, and this is what we start to do. We get our curve and it's rotated around a point, around a line. So in this case, an axis. So what we can start to get is a shell type cylinder that gets created, and a whole bunch of them getting created inside each other. We have a look at something like that here. Notice a solid here, and you've got all these different shells all together. So you've got a shell on the outside, then you've got one that's smaller on the inside, and another one, then another one, and they all go through till you get this smaller one. So you could take them apart and bring them all in, get them all separate. Out of the we've got 12 there. So but imagine an infinite number together, and then you get those together, and then you get the volume of those cylindrical shells. So those cylinders there that we've created, and we get the volume of those, and once we open them out. So that's what we need to do. So what does it start to look like? Let's start back right at the core. So basically we're going to have some point on our curve, and this is rotated around the axis here. So we've got this area being rotated around the axis. So we can start to, if we did it once, we'd get one rectangle and we'd rotate that around. That's basically what a cylinder is, a rectangle that's been moved around. So we moved it around, we get that one cylindrical shell. Obviously not great in terms of its coverage of the volume, because it doesn't really cover it well enough. So if we start to take more and more of these rectangles, and we start to see there's less and less error there, and then we start to revolve these rectangles around. So there's our representative one. So one of the ones we choose to say, oh, this is our general one, starts to look like that. But what do they all start to look like? Well, you can start to see the pieces inside each other. So we got rectangles inside each other, and they're going to get their volume eventually of this cylinder that gets, or this cylindrical shape, as it's rotated around the y-axis. So that's the idea of a cylindrical shell, and what we want to do is split all those up and find the general value, and then find our volume of the whole lot using integration. So what does that rely on? So basically the idea is that when we take one of those shells, so this is our representative one, when we take that and open it up, we'd open it up and we'd look like a rectangle. And it'd look like a rectangle with some sort of thickness on it. We can tell you that we'd get some sort of thing. So basically we're getting a rectangular prism. Give or take. It's not technically right, but it'll do us to get it. We're able to get these. So if we get our area of our rectangle, we've got our thickness, then we're able to find the sum of all those rectangular prisms that we're going to get. So that's what we start to get. Now, the difference between our rotation. When we start to rotate something here, so this function is, the first one we've got is x squared between 0 and 1. So this area here is rotated around the x-axis. Now, normally when we rotate around the x-axis, we'd take our thickness in terms of x, would be perpendicular to the axis of rotation. Now, because we're rotating, and we're taking our cylindrical shell with the rotation itself, our thickness of our disk there or our shell, starts to become whatever's parallel to the axis of rotation. So this time it's going to be delta y, not delta x. There's the difference between slices, circular slices, and the cylindrical shells. So we've got delta y. Again, what we need is to look at this typical cylinder there and look at, well, what would be our shell when we opened up. We get our distance across there and our height. So what is our height? Well, we look at our cylinder. We've got our point xy there. So that's going to be our generated point anywhere on the curve. So our distance there would be x, and we take that away from 1. So that's where we get our 1 minus x as our height of our cylindrical cross section, which becomes a rectangle. And then we basically need this one, which would be 2 times pi times the diameter, the radius. When the radius is y, because we go across x, up y. So that's where we get 2 pi y. So that's where we start to get that.